Hey, North, Mr. Igler here. This video is going to kick off our second unit on atoms and periodicity. Before we get into that, though, we need to talk about electromagnetic radiation. This should be review probably for maybe everyone, but it's important that we kind of start here because we'll be using these calculations and these concepts throughout the unit. You should be able to calculate wavelength, frequency, and energy of any light waves. Okay, so that's what we're going to focus on today. Electromagnetic radiation, which I'm abbreviating here as ER, is just energy that travels through space at the speed of light, and we think of it as just light. The speed of light in a vacuum is 3.00 times 10 to the 8th meters per second. Notice the meters per second here. The unit is in meters, and that becomes important for calculations. So if we think of light as traveling through space as a wave, we can talk about the wavelength and the frequency. The wavelength would be the distance from one peak to the next peak, and the frequency would be how many peaks pass a certain point in a certain amount of time. So the unit on frequency is actually just per second because it's waves per second. So hertz is inverse seconds, 1/seconds. The wavelength is often given in nanometers, but for calculations we'll need it to be in meters. So which wave is more frequent of these two that are shown? The green one would be, because the wavelength is smaller, and so you're going to get more waves per second. Which has a longer wavelength? That one is obviously the red. Which has a greater speed? They actually both have the exact same speed. Even though this one's going to have more waves per second, the electromagnetic radiation itself is still going to be traveling at the speed of light. The electromagnetic radiation spectrum is a wide range of wavelengths, right? All the way from gamma rays, and it probably goes even, I think it goes even smaller than that, all the way up to radio waves, and it gets even longer than that. The shorter the wavelength, the higher the frequency, and the smaller distance that it typically can travel before being blocked. That's kind of in general, right? Radio waves can travel really long distances, miles and miles. They can go through through walls and so forth. You can still catch a radio station even inside your house because the radio waves are actually light waves that are traveling through the walls of your house. It's important to note that the visible spectrum, what we think of as light, is actually just a narrow range in the middle of that spectrum. Okay, so the way that your cell phone communicates with the cell phone tower is actually via light waves, which seems kind of strange because you can't actually see the light, and it travels through walls and through just about anything to get to the cell tower, but it's really just light that is traveling, and that's how all of our telecommunications work, in fact. I mentioned that the visible spectrum is just a narrow sliver of that, right? Just roughly 400 nanometers to 750 nanometers, which you would write as 4 times 10 to the negative 7th if you were going to convert it in meters. 1 nanometer is 10 to the negative 9th meters. That's kind of an important conversion that you'll use quite a bit. Let's look at some examples. So here's our formula. This formula is given on the formula sheet. So you'll always have this. C is the speed of light, lambda is wavelength, and this is nu, and that's frequency. So if you have a wavelength of 650 nanometers, what would be the frequency? At this point, it's just kind of plugging into the formula, so I don't need to kind of go through this that much. The important thing that you must keep in mind is the units. If you screw up the units, then everything gets messed up. So you have to convert your nanometers to meters. So 650 times 10 to the negative 9th, or you could write that as 6.5 times 10 to the negative 7th meters. And then you're just dividing and solving for nu, which is your frequency. Your unit on there is going to be inverse seconds, or hertz. All right, so what if the frequency is 200 hertz? Calculate the wavelength. Again, same formula. Now lambda is your unknown, and the wavelength that you're going to get out of this formula is going to be in meters because the speed of light is in meters per second. So if you wanted it in nanometers, you'd have to take it times 10 to the 9th. Now what if we have a wavelength of 450 nanometers, and we want to calculate the energy that is emitted? We can't do that with the formula we just used. C equals lambda. This will give us the frequency, but not the amount of energy in that light. We have to actually first start by figuring out the frequency, because from frequency you can go to energy, and H is Planck's constant, 6.626 times 10 to the negative 34th joules per second. So if you're given a wavelength, you have to first go to frequency, and then from frequency you can go to the amount of energy, and energy is going to be in joules. So there's just a few examples of how to do some calculations with electromagnetic radiation. If you have any questions, then obviously write those down. We'll get some practice in class, and then we'll start using this a lot more throughout the unit. All right, this is Mr. Igler, signing off.